Hey, and welcome back to the part 2 of ENERGIS series. In part 1, we covered the basics, what a managed PDU is, the market gap for 10-inch rack solutions, and the feature set that we are building. Today, we will go deep into the hardware design. I will walk you through the schematics, every major circuit blocks, component by component, and I will explain the design decisions, the trade-offs, and the lessons learned. Before we start, I want to tell you again that this project operates with 230 volts, and if you don't have the experience to work with high voltage electronics, do not build this project. All the documentation is on GitHub, schematics, PCB layouts, datasheets, and everything. Links in the description, and now let's start with the system architecture. ENERGIS builds up from 3 boards. The main board is the center of the system. It has the microcontroller, the network interface, power supplies, relay drivers, and all the measurement circuits. The display board handles everything on the front panel, status LEDs, indicators, and buttons for local control. The PEM adapter mounts 8 C13 power entry modules. It converts PCB solder pads to wire terminals. The system has 2 electrically isolated domains. This is critical for safety. The high voltage domain connects to the mains. It includes the relay contacts, the power measurement circuit, and the non-isolated power supplies for the measurement ICs. The low voltage domain is isolated from mains. The microcontroller, the Ethernet interface, the USB, and all the control is here. The isolation boundary is bridged by 2 things. First, it's the isolated AC-DC converter that generates 12 volts for the low voltage side, and the second one are the optocouplers that carry serial data from the power measurement ICs across the barrier. The relays themselves are interesting. The coils are on the low voltage side, driven by 12 volts, while the contacts are on the high voltage side, so the relay provides the isolation between coil and contacts. The signal flow is the following. Power enters through a filtered inlet module. It passes through the relays, and each relay controls one of 8 outlets. The power measurement ICs are sitting in series with each outlet, measuring current and voltage. Those measurement ICs output serial data. That data crosses through the optos to the isolated side, and then a multiplexer selects which channel the MCU reads at any moment. The RP2040 microcontroller processes everything. It talks to the Ethernet controller via SPI. It controls the relays through I2C port expander and the Darlington driver array. And it communicates with the display board through another I2C bus. The user can interact through the web interface over Ethernet, through the front panel buttons, or just via USB serial console. And now let's examine the circuit in detail. So the whole point of this video series is not just to talk about the project and understand how it works, but also to give you some educational content. The brain of ENERGIS is the RP2040 microcontroller from Raspberry Pi. I like to start each analysis with the power. The microcontroller needs 2 voltage rails, 3.3 volts for the I/O and 1.1 volts for the chip's digital core. The package has a built-in integrated low dropout regulator, which converts 3.3 to 1.1 volt, so no extra voltage regulator is needed here. As a rule of thumb, every power pin requires a decoupling capacitor placed as close as possible to the IC. This has 2 purposes. It gives basic filtering against any noise coming from the power supply, and it provides a local supply of charge that the internal circuitry can use on short notice. This prevents the voltage level from dropping when the current demand suddenly increases. There are different religions based on what size of capacitor should be used here. I'm with the 100 nanofarad team, but some engineers use 10 nanofarad, some go up to as big as 1 microfarad. It doesn't really matter. Since these capacitors are sitting close to the power pins, I choose 0201 size, which is really small. Every capacitor here is rated for 25 volt. As a good practice, I usually try to use double of the expected voltage on the capacitor as the rating. In this case, we have 3.3 volts maximum, which means any capacitor can fit above 6 volts. The wiring here mostly follows the hardware design guide from Raspberry Pi. The main deviation here is that I don't trust the 3.3 volt rail enough to serve as a reference for the internal ADC. The RP2040 has a built-in 12-bit ADC. It needs a stable reference voltage, which is in my design created by this buffered precision ADC reference with filtering from the digital 3.3 volt rail. R109 feeds the LM4040, which is a 3 volt 0.5 tolerance shunt reference. This 4.7 kilo ohm resistor sets the reference current to roughly 16 microamps. This can be calculated by subtracting the 3 volt reference voltage from the 3.3 volt supply voltage, which gives 0.3 volts. Using Ohm's law, this is 0.3 volt divided by the 4.7K, which is 16 microamps. The power dissipation is very small, well below a milliwatt, so thermal effects are negligible. The following capacitors are filtering and buffering the reference node. The smaller capacitor handles high-frequency noise, and the larger one smooths lower variations. At this point, the voltage is stable, but the reference itself is not meant to drive the ADC directly. So the next stage is the MCP601 rail-to-rail op-amp, configured as a unity gain buffer. The output is tied back to the inverting input, so the gain is exactly 1. This provides an ideal high impedance input for the voltage reference and a low impedance output for driving the ADC. The output capacitors are buffering the op-amp's output. The amplifier supply rail has a 10 ohm resistor. Its purpose is not voltage regulation, but reducing digital noise on the analog supply. Overall, the ADC sees a buffered low-noise 3 volt reference instead of the noisy 3.3 volt rail, which makes measurement more stable and repeatable. Right next to the buffer circuit, there is a 12 MHz crystal. The hardware design guide states that the RP2040 has a built-in oscillator, but its accuracy is questionable and changes from chip to chip. That's the reason why we need here a separate circuit. The external frequency source can be either a CMOS oscillator connected to the XIN pin or a crystal, which is relatively cheaper and accurate enough. Designing this circuit is easy. Usually you only need a crystal and 2 load capacitors. Sometimes the design also requires a series resistor, which limits the drive current to the crystal and prevents overdriving. I always include it as a precaution because worst case you don't need it and it can be just a 0 ohm resistor. To determine the needed load capacitor value, you need to go to the datasheet and look for the crystal's load capacitance, which is 12 picofarads in our case. This can be achieved by putting 2 equal value capacitors on each side. From the crystal point of view, these capacitors are connected in series between its 2 terminals. Since the used capacitors have the same value, the total capacitance is going to be half. I used 15 picofarads, so the combined value is 7.5 picofarads. And additionally, we also have to consider the parasitic capacitance of the PCB, which can be approximated as 5 picofarads. This is in parallel to all load capacitors, so the final load capacitance will be around 12.5 picofarads, which matches the manufacturer requirement. IC18 is the external flash memory used by the RP2040. It's a 128 megabit NOR flash, which is 16 megabytes. That is far more than the firmware itself needs, but leaves plenty of space for things like web interface and future features without worrying about flash size later. The RP2040 executes code directly from this flash using QSPI in execute in place mode. This means that instead of copying the code into the RAM, the CPU fetches instructions straight from the flash. With 4 data lines active, the QSPI provides roughly 4 times the bandwidth of a standard SPI, which is more than fast enough for code execution. Power is straightforward here. The VCC pin is connected to the 3.3 volt rail, together with a 100 nanofarad decoupling capacitor placed as close as possible to the flash. On the signal side, the flash uses 6 lines. This is the chip select, the clock, and 4 bidirectional data lines. These connect directly to the RP2040 QSPI interface. R111 is marked as DNI. It would act as a pull-up on chip select, but the RP2040 already controls this pin internally, so this resistor is not required in normal operation. R112 is a 1 kilo ohm series resistor on the QSPI chip select line. This pin is used as a bootstrap, which means that the MCU checks the state of this pin during the boot process. If it's logic 0, the microcontroller reverts to boot mode, where the device presents itself as a USB mesh storage. This is how the microcontroller enters boot mode, so we can program it. The design contains a push button for this purpose, but it was only necessary during early programming phase. Obviously, no one wants to put their finger into a box when the 230 volt is living its best life inside. The boot mode can be applied by software, which eliminates this issue and lets us program the flash without, let's say, getting a shocking experience. But more about this later in the software video. The RP2040 has two I2C peripherals. I use both of them. I2C0 connects to everything on the main board. This means the EPROM for storing configurations and the port expander that controls relays and the multiplexer. I2C1 connects to the display board through an FPC cable. The separation is intentional. The main board peripherals are on one bus and the display board peripherals are on the other. Pull-up resistors are 1.2 kilo ohms. This might sound kinda aggressive and strong pull-up values, but it's really necessary due to EMI events. The I2C lines also have ESD protection. These are specialized TVS diodes for data lines. They have low capacitance and they are fast clamping. GPIO 6 through 11 are not used. In my early plans, I wanted to add an LCD display to the PDU, but developing the graphics added an extra layer of complexity without much benefit from it. GPIO 12 through GPIO 15 read the 4 front panel buttons. These are active low inputs with external pull-ups. GPIO 16 through GPIO 21 drive the Ethernet controller through the SPI interface, plus the interrupt and reset pins. GPIO 22 is the PWM output for fan control, which is not used anymore. It served a safety purpose if the test showed that active cooling is necessary. GPIO 23 and 24 are the reset pins for the port expander ICs. GPIO 25 is not used anymore and it connects to an unpopulated resistor. This pin was the buck converter enable signal and it was used when I designed the system sleep mode. GPIO 26, 27 and 28 are ADC inputs. I measure here the USB voltage, the 12 volt DC-DC converter and an external temperature sensor. The process LED on GPIO 28 shows processor activity or heartbeat. It blinks when the firmware is running. It's kind of a simple but useful tool for debugging. The remaining parts here are the USB interface, the reset circuit and the debug interface. The run pin is the active low reset signal for the MCU. I use a 10 kilo ohm pull-up here. The debug interface is wired to a debug header. If you have the Pico debug probe, it can be attached here. The RP2040 has an internal USB PHY. It supports USB full speed communication. USB D- and D+ are connected to the Type-C connector through a 19 ohm differential pair. This impedance matching is critical for signal integrity. The second page shows supporting circuits and connectors around the microcontroller. A Type-C connector is used for USB communication, but only a subset of the Type-C pins are used here. VBus provides 5 volts power from the host, but is detached by R170. The power is locally decoupled with C65 and C66, a 10 microfarad bull capacitor and a 100 nanofarad ceramic capacitor to handle inrush current and high frequency noise. In the development phase, this was coming handy, so I didn't need to power the board through 230 nor 12 volts. D+ and D- carry the USB data. CC1 and CC2 are the configuration channel pins. The 5.1 kilo ohm pull-down resistor here identifies the device as a sink. It means it only consumes power but does not source it. The shield connection uses a standard RC network. C78 is a 4.7 nanofarad capacitor that provides a low impedance path to ground for high frequency noise, improving EMI behavior. R131 is a 1 megaohm resistor that discharges static buildup on the shield and prevents it from floating. ESD1 is a simple ASD protection diode array. The D+ and D- lines are routed as a 90 ohm differential pair to the microcontroller USB pins. The divider is using two identical 10 kilo ohms resistor and it has a 2:1 ratio, so the expected measured voltage is 2.5 volts. The next two headers are for development. Both are marked as do not install for production. RGTG is the short for RX, ground, TX and ground. This carries the UART signals. GDRC is short for ground, data, reset and clock, and this carries the debug probe signals. These headers exist because they were useful during the development process, but now they are not needed anymore since the firmware is stable. The footprints will stay on the board in case debugging is needed later. Next to these, there is a 2-pin header for optional cooling fan. The fan runs from 12 volt and I use here a low side N-channel MOSFET for switching. The MCU can control the fan speed via PWM. The 10 kilo pull down keeps the gate grounded, so external noise cannot turn the FET on. All the components in this section are marked as DNI because thermal testing proved that the fan is unnecessary. The EEPROM gives 32 kilobytes of storage for configuration data, calibration values, channel names, network settings, and much more. The EEPROM is powered from 3.3 volts and decoupled by a 100 nanofarad capacitor. The chip connects to I2C0. Address pins A0, A1, A2 are tied to ground. R128 and 129 gives a bit of flexibility on selecting the address, but since this is the only EEPROM in the design, it doesn't have much functionality here. Based on the datasheet, with all address pins being grounded, the device I2C address is 50 in hex. The write protect pin is grounded, which means that we have full control over the read-write access. The EEPROM endurance is 1 million write cycles per byte, but configuration changes are really infrequent. So the chip will probably outlast the product, except if someone changes the configuration in every hour. The next part is the MCP9700 temperature sensor. The output ADC temp connects to the ADC input of the microcontroller. It outputs a voltage proportional to the temperature. Based on the datasheet, it's 10 millivolts per degree Celsius. At 25 degrees, that means 750 millivolts. During the thermal testing, the boards stay well under 40 degrees at full load. So as a result of this, no forced airflow is needed. This external temperature monitoring became unnecessary, and in the final version, I'm only using the microcontroller's integrated temperature sensor. The final element here is a 20-pin FPC connector. It carries 3.3 volts power, ground, SPI signals, and several GPIO lines. In the final version, both the LCD control interface and the 5-volt rails are legacy signals. R149 is a 3.3 kilo ohm resistor network that provides pull-ups on the connected signals to keep them in defined state during reset and startup. R147 is a 1 kilo ohm pull-up on the display reset line. In the early version, this was set to a standard 10K value, but the tests and the real-world usage showed that the surrounding EMI noise is able to reset the display board when a relay is switched on. And a funny story, I literally spent a whole week finding the root cause of these mysterious display reset events, and after I have changed this single resistor to 1K, it magically solved all the reset issues. But let's go now to the next page, and it's gonna be more interesting, not installed parts. IC20 is the W5500 Ethernet controller. It offloads the networking side, the RP2040 talks to it over SPI, and the controller handles the Ethernet link and the protocol work internally. The SPI interface is the usual as always, 4 wires plus an interrupt plus a reset line. R145 is a 4.7 kilo ohm pull-up resistor on the reset pin, and it keeps the reset line high during normal operation, so the IC runs continuously without unintended resets caused by noise or a floating MCU pin. The IC uses its own 25 MHz crystal with C86 and 87 as a 18 picofarad load capacitor. R144 is a 1 megohm feedback resistor across the crystal pins, which helps the oscillator to start reliably. R143 is a 12.4 kilo ohm resistor on the external resistor pin, which is a required reference resistor for the internal analog circuitry, and it's just taken straight from the reference design. On the phi side, the transmit and receive differential pairs go out as transmit and receive with both positive and negative wires. Each line has a small 3.3 ohm series resistor close to the IC with the purpose of edge damping. The Ethernet phi biases the transmit and receive pairs differently. On the transmit side, the TX differential pair is biased directly to the analog 3.3 volt rail. Each line is connected through a 49.9 ohm resistor to the 3.3 volt, which sets the transmit common mode voltage locally at the phi. On the receive side, the RX pair is biased through the RCT node, which is just a short for receive center tap. The two 49.9 ohm resistors set the common mode level for the receiver side, and C79 AC references this node to the ground to stabilize it and to reduce noise. C81 and 82 provide DC isolation between the PHY and the magnetics, and it is required for Ethernet signaling. For status signaling, activity LED and link LED are used. The controller also needs its internal rails to be decoupled. The 1V20 pin has a local 100 nanofarad capacitor C84. The TO cap pin uses a 4.7 microfarad capacitor C85 as required by the datasheet. The Ethernet jack is a shielded RG45 connector with integrated magnetics. The magnetics provide galvanic isolation between the cable and the board. The two already mentioned LEDs indicate status. A green LED is for link, a yellow LED is for activity. The IC drives these LEDs directly. R141 and 142 are 470 ohm current limiting resistors. The shield connects to the ground through a filtered network made by a 1 nanofarad 2 kV capacitor and a 1 megaohm resistor. The W5500 has separate digital and analog power domains, and they must be isolated from each other. The main 3.3 volt rail feeds the digital section directly. The analog section is powered from a separate rail called 3.3 volt A, which is created from 3.3 volt using a ferrite bead. This bead isolates the high-frequency digital switching noise from the sensitive analog and PHY circuitry. On the digital side of the bead, C88, 89 and C90 provide local decoupling for the digital supply. On the analog side, C91 through C96 are all 100 nanofarad capacitors placed as close as possible to the chip's analog power pins. In overall, the Ethernet controller design follows the W5500 reference design. The next page shows the DC-DC converters that generate supply voltages from the 12 volt input. Here the 5 volt buck is not used anymore, but it has the same structure as the 3.3 volt part, so let's focus on that. This buck converter generates the main 3.3 volt rail from the 12 volt input. It uses the MP2315 synchronous buck converter. The IC is rated for up to 3 amps continuous output current and switches at fixed 500 kHz. On the input side there is a 22 microfarad bull capacitor and a smaller 100 nanofarad ceramic. The bull cap handles low frequency current draw, while the ceramic deals with the fast switching edges close to the IC. This follows the datasheet recommendation for input decoupling. R171 and R2 form a simple enable divider. The 33K and the 10K resistors set the voltage on the enable pin to roughly 2.7 volt, which is well above the 2 volt enable threshold. It also avoids applying the full 12 volts on the enable pin. R172 is an optional jumper for an external enable control, so the rail can be turned on or off from the MCU if needed. The MP2315 uses an internal 0.8 volt feedback reference. The output voltage is set by the resistor network around the feedback pin. The 40.2K, the 12.7K and the 33K forming the recommended T-type divider. Plugging those values into the datasheet equation gives an output of approximately 3.3 volt, which matches the target rail. L2 is a 4.7 microhenry inductor rated for 3.5 amps. This value keeps the inductor ripple current around 30% of the load current, which is a good efficiency and transient response trade-off. On the output side, C15 and C18 are both 22 microfarad ceramics. In parallel, they provide enough capacitance to keep the output ripple low and handle low transients without relying on high ESR electrolytics. The bootstrap network consists of a 100 nanofarad capacitor and a 10 ohm resistor. This supplies the high side gate driver and limits the inrush current into the bootstrap cap. R5 and C7 set the AAM pin behavior. R5 is a 100K to ground, which enables light load power save mode. This improves efficiency when the load is low, which is useful for idle or standby conditions. Finally, the green LED is a simple power good indicator for the 3.3 volt rail. With a 1K resistor and a 3.3 volt power supply, the LED current is a couple of milliamps, which is more than enough to be visible without wasting power. So we rushed through this section, but to keep the channel educational, let's see in detail why these values are here. And to do that, we need the datasheet. We have some constants. 12 volt is the input voltage, we want 3.3 volt output voltage, the switching frequency is 500 kHz, and the expected feedback voltage on the feedback pin is 0.8 volts. Luckily, the datasheet contains every values, but it's worth a sanity check. The MP2315 uses an internal 0.8 volt reference, so the output voltage is set by the resistor network around the feedback pin. The datasheet gives the relation. R2 equals R1 divided by V out per 0.8 minus 1. Let's take R1 as the recommended 40.2K and plug the wanted 3.3 volt as V out, which makes V out divided by 0.8, which is 3.3 volt divided by 0.8, which will be 4.125. Subtracting minus 1 from this gives 3.125. So R2 is 40.2K divided by 3.125, which is 12.86K. The nearest standard value is 12.7K, which confirms the datasheet's recommendation. The inductor and the output current also can be checked. The datasheet recommends 4.2 microhenry, but I choose 4.7 microhenry because during the design phase there was no high current 4.2 microhenry option available at GLC PCB assembly. For a buck converter in continuous conduction mode, the inductor ripple current is delta IL equals V out times V in minus V out divided by V in times the inductor value times the switching frequency. The numerator is 3.3 times 12 minus 3.3, which gives 28.71. The denominator is 12 times 4.7 microhenry times 500 kHz, which gives 28.2. This gives a delta IL peak-to-peak ripple current of 1.02 amps. A bigger inductor gives a smaller ripple current, less output ripple, easier EMI, but slower transient response and usually a higher DC resistance. We can also check the peak current, which is I out plus delta IL divided by 2. Delta IL is the previously calculated 1.02 amps, and this is divided by 2 gives 0.51 amps. So the inductor peak current is 0.51 amps plus the output current. And keep in mind that the inductor saturation rating should be comfortably above that. In our case, that's 3.5 amps, so we are well inside the rating. And now just let's get back to the schematic and finish this page. IC21 is also not used anymore. The only relevant part here is R169, which connects the 3.3 volt supply to the 3.3 volt microcontroller supply. In overall, there is no dedicated power sequencing in this design. After 230 volt AC is connected, the 12 volt AC-DC converter starts to work and supplies power to the 3.3 volt buck converter. And this brings us to the next page, where we can jump right into the high voltage part. This block generates the 12 volt DC from the AC input using the encapsulated flyback converter. The design supports two compatible AC-DC modules, one rated at 10 watts and the other one at 15 watts. Only one module is populated at the time, depending on the availability. The footprint and the connections are shared, so the parts are interchangeable without changing the PCB. The module takes the ACL and ACN directly and provides an isolated 12 volt DC output. On the output side, C10, C13 and C16 are 100 microfarad bull capacitors. They smooth the flyback output and provide energy storage for low transients. D16 is a TVS diode on the 12 volt rail. It clamps the overvoltage spikes and protects the downstream electronics. J8, 9 and 10 are solder jumpers used to split the 12 volt rail. They separate the 12 volt supply that feeds the downstream DC-DC converters from the 12 volt supply that feeds the relays. In normal operation, these jumpers are closed, but they allow rails to be isolated for testing, debugging, or current measurements without cutting traces. R150 and the green LED form a simple 12 volt power indicator. And finally, R94 and R95 create a voltage divider, so the 12 volt rail can be monitored by the ADC. The power measurement ICs need 5 volt power supply, but they are referenced to AC neutral, not to the isolated ground. This is a tiny offline 5 volt power supply built around the MP150 and it is not isolated, meaning that the 5 volt is mains referenced and must be treated as really dangerous in the design. This whole 5 volt 200 mA supply follows the MP150 datasheet reference design. The input is rectified with a single diode, so it is half-wave rectified. C35, the 2.2 microfarad 400 volt capacitor, is the bulk storage for the rectified mains. A 39 ohm resistor is there to limit the surge and the inrush current. If you look at the worst case, right at the plug-in when the capacitor is empty, the peak mains is about 325 volts. The initial surge current is roughly 325 divided by 39, which is about 8 amps peak, so this resistor needs to be really big. This IC runs as a tiny high voltage buck converter. It charges its own VCC at the startup and then regulates normally from the rectified bus. The output stage is a 1 mH inductor with a 100 and a 1 microfarad output capacitor, matching the typical applications type from the datasheet. And finally, R96 is a 10K minimum load and discharge path for the 5V rail. It draws above 0.5 mA at 5V, so it keeps the output from floating and helps with discharging when the power is removed. The lower part is a 1-to-1 copy of the previous non-isolated 5V supply. The reason behind this is that one measurement IC consumes about 30 mA. With 8 outputs, that is 240 mA total current consumption. The circuit is only capable to supply 200 mA/ish, so the second stage is necessary, and it's also giving some extra headroom. The next page is going to be a fast one. The device has 8 relays and each relay controls one outlet. I'm using power relays here with 12V coils. The contact rating is 16 amps at 250V AC. Since each relay has the same circuit, let's just check one. The coil connects between the positive 12V supply and the driver output. When the driver pulls its output low, the current flows through the coil and this energizes the relay and the contact will close. 230V is connected to one of the contacts, and when the relay is switched, the 230V appears on the output. D1 through D8 are flyback Schottky diodes. When the relay coils turns off, the magnetic fields around the coils collapses. The energy, which was stored in a form of magnetic field, induces electrical current, and this creates a voltage spike. Without the diode, that spike would flow back to the driver and it would destroy the driving transistor. The diode clamps the spike to about 0.4 volts above the supply. Schottky diodes have lower forward voltage than standard diodes, and they respond faster, and generally they are better protection for inductive loads. Right next to the relays, the output measurement is sitting. For output monitoring, I'm using the HLW8032, a single-phase AC power measurement IC. It measures the line voltage and load current simultaneously, then internally computes the useful stuff, the RMS voltage and current, the active power, and the energy. It can report data either as a UART serial stream or as a pulse outputs proportional to the power/energy. Each circuit is powered from the non-isolated 5V power supply, so all the measurements are referenced to neutral. This IC has 3 analog inputs. IP and IN are differential current sense input pins, and VP is the voltage sense input. On the output side, TX is the UART transmit from where I read the data, RX is not used according to the datasheet, PF is the pulse output, but I'm not using it since all the needed data available on UART. The current is sensed with a 2 milliohm shunt. The IC measures the voltage drop across this shunt using its differential inputs. Both sense lines goes through a low-pass filter made up by a 1 kΩ resistor and a 33 nanofarad capacitor for filtering. At 10 amps RMS, the shunt drop is 10 amps times the 2 milliohm shunt resistor, which is 20 mV RMS. I could have used the 3 milliohm resistor here because the current input at full scale is 30.9 mV RMS, but the hardware itself was designed to be able to work on European and US grid too. In Europe, the output connector is officially rated at 10 amps, while the same connector is rated at 15 amps in the US. At 15 amp RMS, a 3 milliohm resistor would create a drop of 45 mV RMS, which is above the 30.9 mV RMS full scale input. With 2 milliohm resistor at 15 amps, the input is 30 mV, so it will stay in range. Voltage is measured through the VP input using a high value divider. The top leg is 4 470 kΩ resistors in series, 1.88 megaohm in total. The bottom resistor is a 1 kΩ to ground. That gives a divider ratio of about 1880 to the 1. At 230 volt, VPCs are 230 divided by 1880, which is 122 mV RMS. On 120 volt, this value is 64 millivolts. The full-scale input voltage limit is plus minus 495 millivolt RMS, so the voltage sense is well inside the range. The 33 nanofarad capacitor here has a filtering purpose for the voltage sense signal. This design uses the UART output. The TX pin goes to the optocoupler, and from there the microcontroller reads the frames and extracts the measured values. The next page contains the same circuit for channels 5, 6, 7 and 8, so let's skip that and let's see now the optocouplers. I'm using two 4-channel optocouplers. This takes 4 logic level signals from the measurement side and reproduces them on the digital side, but with galvanic isolation in between. The datasheet rates the isolation at 3 kV and the device is a phototransistor type with a CTR specified at 5 mA. CTR is the current transfer ratio. This is the ratio between the LED current on the input side and the transistor current on the output side. Higher CTR simply means you get more output current for the same LED drive current. On the input side, each UARTX line drives an LED. Each channel has a 1K series resistor and also 1 nanofarad capacitor to ground. This provides a bit of high frequency filtering and edge softening. If we look at the numbers, the measurement rail is 5 volt, the LED forward voltage is about 1.2 volts, and since the series resistor is 1K, the LED current is about 5 volt supply minus 1.2 volt forward voltage divided by the 1K resistor. That is roughly 3.8 milliamps per active channel. As per the datasheet, CTR is specified at 5 milliamp LED current, so this is close to the intended operating point. On the output side, each channel is a phototransistor. The collectors are pulled to 3.3 volt by a 10K resistor. The emitters are tied to the digital ground. This makes each output an open collector style signal. When the opto is off, the 10K pull-up holds the line high, while the opto is on, the phototransistor pulls the line low. When the transistor pulls low, the current is 3.3 volt divided by the 10K, which is about 0.33 milliamps. This is comfortably within what the optocoupler output can handle. The second opto is exactly the same, but it isolates the TX data for the channels 5, 6, 7 and 8. The next page ties together the relay control and the measurement signal routing. The MCP23017 I/O expander gives 16 extra digital pins over the I2C bus. The supply voltage is 3.3 volt with two 100 nanofarad decoupling capacitors. The I2C address is set by 3 address pins. Here they are tied low, so the base address is 20 hex in 7-bit form. Reset is another control line which gives deterministic recovery path. If the I2C bus gets stuck or the expander ends up in a weird state, you can hard reset it and reconfigure it clearly. On the IO1 group, 8 pins drives the input side of the relay driver. There are 100K pull-downs on each output. That forces a defined off state during reset and power up. It also prevents relay chatter if the expander pins are still in high impedance. On IO2 group, 4 pins generate the multiplexer control signals. 3 pins are the A, B and C address bits and 1 pin is the enable. This lets the firmware select which channel is connected to the microcontroller's UART port. First, it sets the A, B and C pins, then it enables the multiplexer. The ULN2803 is an 8-channel low-side driver. It takes the 8 relay control signals and switches the relay coils by syncing current to the ground. This is a current device, not a logic device. The relay coils are on the plus 12 volt rail. The driver pulls the low side of each coil to the ground when enabled. COM is tied to the coil supply. That enables the internal clamp diodes. When the coil is turned off, the stored energy is dumped through the clamp path instead of punching the driver. It's the same principle as the Schottky diodes we've talked before. There are 0 ohm links on the outputs, but these are not there for resistance, they are there for a very light isolation and serviceability. The 74HC151 is an 8-to-1 data selector with full binary decoding. This selects one of 8 UART transmit sources from the optocouplers and routes it onto the shared TX line. The selection uses 3 inputs A, B and C. The G strobe input must be low to enable the multiplexer. When the strobe is high state, the normal output is forced to low state and the inverted output is forced to a high state. On the output side, the solder jumpers serve no electrical purpose. They are leftovers from early debugging phase. Many times I'm not sure if I cross the TX RX lines or not, and this configuration gives a flexible possibility to select the data path instead of ordering a new PCB version. The transmit signal is also buffered with a small op-amp. An op-amp buffer has a very high input impedance, so it doesn't load the signal source, and a low output impedance, so it can drive the next stage cleanly. The LED current is set by a 1K series resistor. On a 3.3 volt rail with a blue LED, the current is in the low milliamp range. It is bright enough for a status indicator. The local 100 nanofarad capacitor is there to decouple the power supply of the op-amp. And yes, basically that was all, at least for the main board design. There are two smaller PCBs left, so let's get through them quickly. And let's see now the display board. The display board schematic is simpler. I'm using two MCP23070 port expanders to drive LEDs. Both are decoupled by two 100 nanofarad capacitors. The display expander controls the main status LEDs. The device address is set to 21 hex by pulling the A0 high. Port A drives 8-channel indicator LEDs. These show the on-off state of each outlet. Through 1 kΩ resistors, the LED current is about 2 milliamps. The LEDs are labeled channel 1 through channel 8 and chosen to be green. Port B serves as a visual feedback for the system status. The error, the Ethernet, and the power LED are driven from here. The selection expander controls the channel selection indicators. The wiring is the same as before, except the device address pins. The device address is 23 hex. Port B is not used here, all the LEDs are connecting to port A. These LEDs show which channel is currently selected on the front panel during manual operation. Both expanders connect to I2C0 from the main board. In the next page, a 40-pin FPC connector for the LCD module is still visible in the schematic, but the connector and all surrounding components are marked as do not install, since no LCD is used anymore. The components are still present because I wanted to keep the design universal for future use. An alternative 4-pin header is available for the well-known I2C OLED displays. Again, this feature is kept for future use, or maybe for someone who wants to experiment and add new features to the PDU. The 20-pin FPC connector receives signals from the main board. The pinout is 2 pins for the 5V and 2 pins for the 3.3V, from which the 5V is not used anymore. The I2C SDA and SCL for the port expanders, for button signals, and the rest of the pins are not used anymore, they carry the LCT control signals. The last pin is the reset line for the port expander ICs. D5 is an ESD protection component. On the last page, 4 tactile switches are there for user input. Each button circuit is identical. One side of the switch is grounded, on the other side it is pulled high by 10K resistor to 3.3V. Each button has a 100 nanofarad debouncing capacitor and a TSV diode to protect against ESD events. The 4 buttons are right, left, OK and power toggle. And we arrive to the last PCB of this project. The PEM or the SPAM adapter is the simplest board in the whole design. This adapter board exists because of a supply chain issue. Commercial snap-in C13 modules are using bus topology, which means all neutrals, all lives and all grounds are connected. Individual switching is impossible with those. The used shooter modules have individual pins, but they are designed for PCB mounting. The adapter board converts the PCB mounting to wire termination. Each module has 3 connections. L is for live, N is for neutral, and PE is the protective earth. This module is soldered to the power entry module, and on the other side of the PCB I have standard 6.3mm fastened wire terminals, so the main board terminals can be connected to the output connectors. And that was the schematic deep dive for ENERGIS. We went through the main board, the measurement, the isolation path, then the display board and the PEM adapter. Again, this project deals with mains voltage, so if you don't have the experience around high voltage, don't build it. The next episode is part 3, the PCB layout. I will walk you through the board, where the parts go, how the mains area is kept away from the low voltage area, and the key routing choices. At the end, we will assemble together a working unit. All files are available on GitHub, schematic, layout, and the documentation. Links are in the description. Thanks for watching.